here pretty quick. So unless you have a really perfect resume, I mean, all of us you could probably all need help a little bit on resume building. And so it's going to be the 21st, and we'll have folks here from the campus helping you to navigate a resume, make it better, give you tips and stuff like that. And so it's going to be a fun workshop. It'll be here in the building, and so you don't have to RSVP or anything for the workshop, but definitely recommend it. I did put a link on our main page because we have so many events. I did put a link on our main page here on Save the Dates, CIS events, which has a list of all the events we have throughout the semester, including the March 21st resume writing one. But they're all in here to where you can see it on one page, all the events we have coming up. And all of them, except for the coding with robots, all the other ones are totally free. And so, questions before we go on? Awesome. All right, so this week is week 4, transmission basics. And chapter 3 is what we're going over. And we're going to look at all the different transmission medias tonight as we discuss it. We'll end with the ping lab and tracer route lab. Homework is review questions always for chapter 3, quiz for chapter 3 on transmission basics and media. Definitely do your reading before you do the review questions and quiz. It'll help you tremendously when you're doing those. If you don't, you're forced back into text anyway. And so however you want to do it. So transmission media and basics of transmission media. We'll look at some transmission media concepts tonight, including full duplexing, attenuation, latency, noise. We'll describe physical characteristics of coaxial cable, STP, UTP, and fiber optic. If you look at the back of the room, actually, those the blue, red, and white cables are your STP, UTP that we'll be talking about, untwisted pair. And then we'll compare the benefits and limitations of the networking, different networking media. So like fiber has certain benefits over twisted pair Ethernet. Coax has certain benefits over Ethernet and fiber. We'll look at the principles on serial connector cables and some wiring basics for buildings and work areas. So transmission basic, everything we do today, whether mobile, desktop, laptop, all is transmitted. Whether you see it or not, doesn't matter. It's there. The transmission media is there. The media can be invisible through wireless, or it can be visible through Ethernet, coaxial cable, fiber optic. But basically, the transmission part is issuing signals. And it does have a small amount of electrical current in those signals, in all signals, whether it be Ethernet, fiber, or even over the air. Everything in the universe is made up of electrons. And you learn that in science when you're going through school, and neutrons and electrons. And we can't see them, but they're there. And so that's what this technology uses. The networking basic uses this transmission signaling. And the transmission itself is a process of transmitting signals signal process after they've been transmitted. And the transceiver receives that signal. So you have the transmission, the transmission, and the transceiver all in that play. Important data transmission characteristics when it comes to signaling. There's 2 different types, analog and digital we'll talk about here. Volt, the word volt is a car, by the way, Chevy Volt, but it also in networking deals with current, the current going through whatever media it might be, electrical current. The electrical signal strength is directly proportionate to the voltage and the signal voltage. And signals can be either these criteria: current signals, light pulse signal, and electromagnetic wave signals. So here's an example of an analog. You'll notice on an analog, the lines are continually moving like a wave on analog. It never really stops. Even if it's really low, it's still moving somewhat in an analog system. The voltage varies, as you can see, but it's continually. And the properties of analog is amplitude, frequency, wavelength, and phase, which we'll talk about. So amplitude is a wave strength. Frequency is the number of times the amplitude cycles over a fixed time. It's measured in hertz. The wavelength is a distance between the peaks and valleys on the cycle points, and it's inversely proportionate to the frequency, and it's expressed in meters or feet. So here's an example of waves on a 90-degree phase difference. One of the things that you might notice is it's fairly fixed, this here is, as far as the peaks and valleys, and it's, again, it's just for diagram purposes. But all this is showing is that over time, analog is pretty stable, all right? Anybody remember having analog cell phone way back when, before digital? Anybody remember those days? And you could be talking to somebody, and as the signal got weaker, you would get garbly and you know kind of breaking up, right? But it's still there. The signal is still there. We'll find out why that is in a second. But analog signal benefits over digital in the fact that it's more variables, meaning you can, like in the cell phone I just mentioned, conversation, even though the signal's super, super low, you could make out sometimes what people are saying, okay? Convert that to digital or to data world, to networking, data would break up and lose connections, but it would pick it up and continue on the journey. The drawback of analog signal, though, it's varied and imprecise voltage, meaning a lot of transmission flaws, a lot of noise susceptibility, drops of data. The digital signals, these are pulses of voltages, and we're switching now from analog to digital. Digital is basically, this is a good example of digital. Come over to the light switch, and on and off, that's digital. 0, 1, 0, 1, 0, 1. 0 being off, 1 being on. That's it. That's all you have. There is no waves that you have in analog. And here's what a digital looks like. As you can tell, it's either on or it's off. It's on or it's off. And so in a digital world, both for networking and since most of you are used to cell phones, when you're out of range or out of signal range, you have no signal, that's it. You can have one bar and generally call somebody or get data super slow. When it goes down to no bars, that's it. There is no, you don't get anything, right? And so, and by the way, the bars on your phone have nothing to do with whether you can connect or not. Well, it does, but it has more to do with the strength of that connection. So once you get that one bar, you are connected. It's just how fast is that connection. So zeros and ones, the reason it's represented this way is because that's what computers understand, okay? Computers are pretty stupid. We put data in or program stuff in, and it does what we tell it to do. So if something's not working, it's either been programmed in wrong, or there's something broke or breaking in the hardware software of a computer, right? So it's not going to do anything out of the ordinary. It's not possessed. It doesn't have a mind of its own. It's going to do what it is told to do, both in networking, programming, and whatever it is you want to look at. So it's black and white, zeros and ones in digital world, in digital pulses. This slide just shows you the equivalent of a byte and breaking it down a little bit. So a byte is basically 8 bits together, okay? 8 bits make 1 byte. Computers read and write that type of information using bits and bytes, and to find like a decimal value of a bit, you multiply 1 or 0 by 2 times. So in the example here, in an IP octave, the first octave we'll say is like 192. You might be familiar with that from your home Wi-Fi. 192.168.1.1, something like that, right? So we'll just pretend that this is one of the first octets, like a 192 or something. And so we go in there and each one of the numbers then, like a 1 and the 9 and the 2, those are decimal. Converted to binary, it's going to look something like this. So every octet is going to have 8 places starting with 0. The 7th bit position, all of them you'll notice is 2 to whatever power. Okay, starting with 7 all the way down to 0. Okay, and it doesn't change. The equivalent value, decimal value, is there at the bottom: 128, 64, 32, 16, 8, 4, 2, and 1. And there is one of the weeks we do here in a bit where we actually show you how to convert binary IP address to decimal IP address, decimal IP address back to binary IP address. And the reason you need to know that is when you're converting or setting up a network and you're getting into setting up a subnet mask is what it's called, you need to know how to do that, all right? And you'll learn more about that this semester. But basically on analog and digital, converting byte to a decimal is important because it determines the value of each bit, as mentioned in the screen earlier. It adds the values. Then converting decimal to byte is a reversing process of binary to decimal. So it's decimal to binary. And then on the conversion itself, you can do it by hand or calculator. I'll show you how to do it both ways. I was taught do it by hand for years, but everybody has a smartphone that has a calculator built into it where it can do the conversion for you. And so it used to be called scientific calculator. They don't call that anymore. Sometimes your phones might call it programmer calculator, and it just literally has 0 and 1 button enabled, and that's it. Where you type in multiple zeros and ones, then you hit bin or DEC for decimal, and it converts that binary into decimal. And then you can type in decimal number, like 192, and then hit bin on your calculator, and it'll convert that decimal to binary for you. Digital signals benefit over analog because they're more reliable, less severe noise interference like analog. Analog would literally could be interfered by engine noise, magnets of any type. If you had, which some of us do, have more electrostagnetic energy where we're constantly shocking people. Anybody like that in here? Or you're shocking yourself? Or whatever the case may be. Weather, buildings with steel. Analog had a major deal with all those. And a whole bunch of other different types of interference. But overhead, basically, on this is the signaling as non-data information built into it required for proper signaling, routing, and interpretation. And the non-data would be like, an example would be your source IP and destination IP would be an example of non-data, all right? That's just giving route information. So if I'm here right now and I send you a file, in that file transfer data is going to be, part of that package is going to be not only the data, but part of the non-data is going to be my IP address, your IP address. My MAC address, your MAC address. Make sense? It's going to be in that format. Data modularization. What this is all about is data relies on data transmission or digital transmission. We already found out that digital transmission is comprised of zeros and ones, on or off, that's it. The network connection may handle only analog signals. So because of that, you'll need modularization to where it can convert analog to digital. An example would be AT&T dial-up DSL. Anybody ever had that before at home? AT&T dial-up or AT&T DSL? That is converting, or anybody have a regular phone at home that you don't have digital phone, you have a regular phone you pick up? Literally nobody. Okay. Do you remember the days where you had a phone you picked up that was analog at home? Okay. Okay, so now we're getting somewhere. So way back before, like 5 years ago, but way back when I was a little kid, no, just kidding. So way back in analog days, whenever you would have dial-up, like through, or let's say DSL, which wasn't dial-up, the signal coming to your house from analog phones it's analog technology. But to get it to your computer to work, you got to have a modularization, which are your modem, which will convert that analog into digital. And then when you would do stuff on your computer, it would then convert that digital back to analog to go through the AT&T lines to get where it needed to go. So the modem accomplishes the translation part of analog digital, digital analog. It's kind of like, I guess, you could actually relate it to maybe, I don't know, the recent conversion of digital TV, where you had to get you got rid of the UHF, VHF antennas, and now we had to get a digital antenna because that's all the stations now have. And you had to get a digital conversion box if you had an older TV, right, to convert the digital signal coming from the station to your old analog TV. And maybe some of you did that, I don't know. And the TVs really wouldn't have to be that old, really. It wouldn't have to be super duper old to not be able to convert or not have digital built in, just analog. And you needed a digital box to do it. And that was just to watch over-the-air TV from the 3 stations here, 10 stations we can get here if you go up to Madison. So data modulation is a technology that modifies analog signals to digital, basically. And it makes it suitable to carry data like internet. And in that internet package is going to be everything that you do if you have that type of package at home or at work, where it converts the analog to digital to data, which would be music, movies, text, whatever it is you're sending across the lines. So here's an example of different frequency modularizations that could occur. You've got basically at the top the carrier wave, and notice over time it either goes up or down on the wave. Next, the information wave, it's more elongated and pretty static. Then the FM wave, which is again FM radio, like you're probably familiar with, much closer together. And FM radio, again, you can send data, by the way, through FM signals. Well, you do send FM. If you listen to FM radio, it is being sent to your, to your receiver that you're listening to in your car or at home. But when you think of data, you don't think of music, but that is data. Or if you don't think of voice coming across a talk radio show as being data, but it's data being converted. But what's cool about FM is you literally can send files via FM, believe it or not. If you have the right data, modularization, demodularization set up, you can literally send files over that same FM wave that you can. Now, it's very slow, and it takes a long time, but it can happen. So here's some different types of transmission we're going to talk about. Simplex, half-duplex, and duplex. Simplex is basically single transmission, one direction. I'm sending something somewhere, okay? Half-duplex is a single transmission, is both directions, one at a time, one communication channel, shared from multiple nodes to exchange information. Full duplex is a signal transmission, both direction, all the time, using on data networks specifically today. Would be the full duplex. So left, simple, middle, half duplex, and right, full duplex, where everything's in full, receiving and sending, continually, receiving and sending. So the channel basically distincts between the different paths, between the nodes. An example I could give you on channeling that you might understand is your Wi-Fi access point at home. You might have seen in your router how it has different channels, like maybe 1 through 11, right? Each one of those channels falls upon a different node for that Wi-Fi to travel. Okay, so if you have a wireless audio system at home, that's the surround sound, that's on channel 6, on the same gigahertz as your Wi-Fi access point, and say it's on channel 6, you can have collision to where one of the two drops and doesn't work, like your mobile phone or your laptop. Simple solution on that is changing the channel on your Wi-Fi access point from 6 to say 1 or 6 to 11, because you cannot change the channel on your generally can't change your channel on the audio system because it's built in factory. Okay, does that make sense? Some of you might have had that happen because I think wireless surround sound is pretty popular because why get wired if you can get wireless and it's not that much more expensive. But it generally does fall upon channel 6, like I mentioned. And if you have wireless at home, which most of you do, and you have collisions, meaning, why is my wireless dropping when I'm in the living room? You could be on the same channel, channel 6. Change it to something else in your Wi-Fi access point. And we will go over access points in here and kind of some of the interfaces, like for Linksys, which is the main one, on how to do that. But it's really not that hard to do. And if you wanted to get help before that, we go over that, you can just email me and I can send you steps how to do it. So full duplex advantage is on the right side, increased speed because everything's flowing to and from. You're not waiting for something to be sent before you can receive, since it's only that would definitely be the case in both the simplex and half duplex. On full duplex, you can be sending something before you receive something, and vice versa. It's continually flowing back and forth. So multiplexing is basically where you have multiple signals traveling simultaneously over one medium. An example would be coaxial. Example would be Ethernet, like we have in here. Example would be fiber. And Wi-Fi also. Subchannels is where you basically take the network and subdivide it into multiple subchannels. In networking, we call that subdividing the LAN, multiple virtual LANs. Like an example here on campus, we have a separate channel for data and a separate channel for voice. The voice would be the phones, which our phones are connected to the network here on campus, but it's the same network as our computers are connected to. But in order to talk to one another, they have to be on separate subnets or separate channels, you could say. And so multiplexer is basically where it takes those channels and combines them into one device to manage them. And then demultiplexer, it separates the combined channels and regenerates them on the other end. So here's an example of what's called time division multiplexing, where it takes the divided channels and multiple time intervals and puts it back together. All you need to know about this is, on the left side, data is being sent in different channels. On the right side, it's being put back together and sent to those unique channels to be delivered. Statistical multiplexing is where transmission assigns slots to nodes according to priority. And it's more efficient because it's falling upon different nodes of the transmission. An example would be what I just mentioned here on campus, the node voice, totally separate from data. Now, there was a time about 20 years ago, we were what's called a flat network. A flat network means the data and the voice all flowed through the same channel. So what would happen is at noon, if I got a call from somebody, sometimes that call would be intercepted and dropped because people was at lunch doing what at lunchtime? What do they do at lunchtime? Anybody? What do you guess? Lunchtime, you're in front of your computer, what are people doing? Eating their lunch, what are they doing? Searching the web, right? eBay, man. You gotta do some back to Facebook over there, but eBay was big back then. Huge, man. Huge. eBay. eBay was humongous. And so eBay took up a lot of data, online shopping. At that time, I think it was, what was it, MySpace? Yeah, MySpace. Remember that? What else was back then? Social media. I think that was MySpace. What was another one, too? I can't remember. Somebody help me. Back in, this would be 2001, 2002. MySpace was definitely one of them. I can't remember the other one off the top of my head. It was one that high school, college students used, more so than MySpace. Napster was another one that was used back then. So anyway, it would help because we're on a flat network, we weren't on a multiplexer network or a subdivided channel network, we had collisions. And so around 2002 is when we subdivided our network to where data flowed more efficiently without collisions. Frequency division multiplexer, all you need to know about this one is it takes data, and you can just say, for argument's sake here, for example's sake, the blue and red, blue is data, and red will be voice. The bottom one we won't even pay attention to right now. But blue and red, the top and middle, top data, voice in the middle. As it goes across, it goes out into the multiplexer. The demultiplexer would be like the phone. When I pick it up, it's converted that analog signal from my wife that called on campus, that, but believe it or not, when she calls on campus, it goes through the analog phone patch wall, into the digital, to when I pick it up, it's demultiplexed and put back together to where I can hear what she's saying. Okay? But it's being converted through that whole process. This one here basically is referring to fiber optic. Fiber optic, the only difference is longer distances and much faster in fiber. Longer distances, much faster, and better noise resistance, meaning fiber is good for like manufacturing, heavy machinery, engines, a lot of electromagnetic energy. You wouldn't want to run Cat5 cable or wireless in those environments because the data would drop. So relationship between the nodes, you've got different types of transmission. You've got point-to-point transmission. Here on campus, before the nursing building was built, anybody remember when there used to be satellite out there, or dishes out there, remember? We use some of those for point-to-point transmission to like some places here downtown Rockford, where it would literally be point-to-point to. Actually, what these did was, this farm here that we had will point to the dish farm on Mulford, and no, I take it back. Yeah, Mulford and Perryville. If you keep driving on Mulford till you get to Perryville, you'll see a whole bunch of contraptions with little dishes on them. It would point it to that, and then from that, it would actually point multiple places in the region to where we were set up to where we could do, I could be teaching in here, it could be videoed, but directly point-to-point stream to another building here in town. And so one transmitter, one receiver on a point-to-point, point-to-multipoint, one transmitter, multiple receivers, broadcast transmission, one transmitter, multiple undefined receivers, used on wire and wireless, simple and quick, non-broadcast, one simple and multiple. So let's talk about a couple of these, all right? Multiple or broadcast transmission, let's talk about that one. You take part of this every day. This one here, the third one. Can anybody think of a media or we'll talk about something you watch every day that it uses broadcast transmission? Anybody think of one? Just take a guess. Yeah, I saw you got TV. Yeah, TV. Yeah, TV. So I'm on WFR, I'm on WREX, I'm wherever, WTVO, and they're broadcasting, right, to multiple people, undefined receivers everywhere. Whatever it can connect to them, whether it be over antenna, digital antenna, or whatever. And so it's one transmitter, multiple. They have a tower. If you drive by these stations, these news stations, they have a tower, huge towers that literally transmit their digital signal. And that would be a broadcast transmission. Now, one transmitter, multiple receivers. Let's talk about that for a second. What do you think, technology-wise, that you use has one transmitter, multiple receivers in your house? One transmitter, multiple receivers. Just bring it down real basic. What in your house transmits something that other devices connect to that something all day long? Wi-Fi, good. It's a good example, right? One transmitter, which would be your Wi-Fi router, multiple, these are defined receivers that you've defined in your network, right? Meaning, if I'm next door, I can't connect to your Wi-Fi network because I'm not logged into it. I don't have an access into it. Put the passcode in it. So it's multiple receivers that are defined, that are connected. That's point to multipoint. Broadcast is where I have one transmitter that undefined receivers can connect to, and TV would fit that bill. The other one to fit that bill would be what besides TV? Radio would fit that bill too as well, right? And so non-broadcast is one transmitter, multiple defined receivers, and we'll look at some of those in a second. So let's look at this. Point to point, I just mentioned RBC there, and let's say one of the downtown buildings for training or something. We did that years ago. Right side, broadcast transmission, TV, radio. Makes sense, right? Now let's talk about some terms you probably heard of with your Xfinity or Comcast bill, or you've been looking at data or text through them. You always hear about throughput when you're buying data for home or business internet, right? What throughput is measures the amount of data that's being transmitted over a period of time. capacity or bandwidth, and the quantity of bits transmitted per second. Like an example would be, your throughput could be, let's say, 200 megabits per second, 500 megabits, 50 megabits per second, 20 megabits per second, whatever. Okay? Bandwidth, though, the strict definition of that is measure the difference between the highest and lowest frequency that's being transmitted and the range of frequency, and it's measured in hertz on bandwidth. And so bandwidth, even though you could have a large throughput and a restricted bandwidth, and really not really matter if you have a larger throughput, because if you have a restricted bandwidth, you can only push so much data through it. It's kind of like having a small funnel, and you're trying to push a lot of water through it, versus a larger funnel with a larger hole, more water through it. And so bandwidth is going to determine the speed of that throughput regardless. So here's an example of throughput measures. You've got like quantity 1 bit per second, complete example 1 bit per second, no abbreviation. BPS is the abbreviation for that one. 1,000 bits per second, kilo, 1 kilo per second, kbps, 1 billion or 1 million, mega, 1 megabit per second, mbps, 1 billion, gigabit per second, 1 trillion, terabit per second. Terabyte or terabit per second is pretty much where we're going when it comes to even Wi-Fi is what the future looking at. But right now we're pretty much in the gigabits per second when it comes to data in a network. Like a gigabit, you might have heard about 1 gigabit transfer rate on Ethernet on a network. Pretty popular. So two types of transmissions we're going to talk about here now. Baseband and broadband. Baseband is where digital signals are sent through DC current. And DC current, you might have heard of as, you might refer that to battery. Like, you think of DC, you think of battery power, you have something low voltage. It's exactly right. It's a lower voltage, it cannot knock you down and shock you like a taser or something. But there is voltage that goes through DC current. It requires exclusive use of the wire's capacity, one channel at a time. Example, Ethernet. And so our Ethernet we have here connected to your computers, that's into switches back there, has a small DC current running through it. Next would be broadband transmission. Broadband transmission would be signals modulated, analog waves, does not encode the information as digital signals do. Noise transmission. Any undesirable influence on the line can cause noise. It could be electromagnetic, it could be engine, weather, heat can also cause it, electric, whatever could cause it. So types of noise: electromagnetic interface or interference, EMI, RFI. Crosstalk is basically good in some cases, like when we do the cable, and we talk more about it. But crosstalk in Ethernet cable is good because you want the wires to touch each other and be twisted. The more twisted they are, the better data attenuation, and the data does not drop. But crosstalk for most other communications, like wireless, not good because it can cause termination, drops data. Crosstalk would be an example where I talked about the wireless sound system hitting your Wi-Fi system at home on the same channel. All right. Also, Ethernet running right next to electrical cable wouldn't be good. Okay, at home, wouldn't want to do that. That would call crosstalk. Environmental influences, heat, even cold can cause problems too. Not just heat, but cold can cause it as well. So here's an example of a crosstalk between cables, which actually is good to have if it's a Cat or Cat5 cable. So basically on this one, we've got the cable on the outside, we've got the wires affected by crosstalk, and then the wire transmission of signals. And we'll say this one here is a PVC pipe, and you're running three different wires through the PVC pipe. We'll say the three that are pointed there are Cat5 cables. We'll say the one that's pointed on the wire transmission signal, we'll say that's electrical right there. That one's electrical. the crosstalk would push out from the electrical wire and hit all the Cat5 cables and definitely cause problems, okay? So generally, like in a classroom like this or a business, when you're running Ethernet from this room to the server rooms, they're all jumbled together, all by itself, away from everything else. Does that make sense? Whether it be in the ceiling or the floor. We generally jumble them by at least, for our case here, we jumble them by room. So like in here, we have like 20 connections or something. So we can literally jumble 20 Cat5s together. We run them from end to end. Then on this side of the room, once the wire's been run and they're coupled together, it's usually like a black tape, or you can put PVC pipe in them. Just as long as they're not nearby any other electrical, they're fine. But then after we've run the wires and put them into wherever we're going, like a drop or a wall unit like this up here, that's when we actually connect them with the connectors after the wire's been ran. And you'll learn how to do that in here when you do the straight and crossover cable. You'll learn how to do the wire crimping, which is a lot of fun. And I've had 100% of people do that, by the way, over the last 18 years. And so I know all confidence you will do that just fine. And you do get to hang the wire around your neck when you're done as a proud, that you did it, your trophy. So here's some transmission flaws that can be caused, or what can cause transmission flaws: attenuation, loss of signal strength as it travels away from the source. Wi-Fi would be an example. Cell phone would be an example, going away from a tower, cell tower. Signal boosting technology. You could have amplifiers in the analog world. Back in the cell phone days, they used to have amplifiers in between all the cell towers to cause the signal to increase. Regeneration. This is where in the digital signal world, where data is regenerated in certain intervals. Okay, an example in the networking world would be if I'm wanting to run my Cat5 from this room to an IT server room that's, say, 100 yards from here. I would need multiple regeneration devices in between, meaning switches, and all that would do is regenerate that connection to cause it to go on. You generally don't want on Cat5 any more than 100 feet, 150 feet of length between drops. You wouldn't want to go 300 yards, wouldn't work. But 150 feet is usually a max. Then you need a switch, another 150 feet, switch, another 150 feet, switch. Because what that's doing basically is taking that data, regenerating it to let it go on further. That makes sense? Because the Cat5 can only go so far. Same thing with fiber, but fiber can go longer distances. Fiber had no problem going to football field distance. No problem whatsoever. Fiber optic is what's used to run underneath oceans. Okay, literally thousands of miles of ocean with fiber. But even with fiber, let's say the longest distance of the best fiber cable is a quarter mile. Every quarter mile would need another regenerator under the ocean to go to the next quarter mile. Or let's say it's 5 miles, every 5 miles. That's a lot of regenerators, okay, throughout the distance. Then amplifiers and repeaters. This would fall underneath the physical layer of the OSI model, along with switches and also routers and your NIC card. So here's an example of an analog signal using an amplifier. And example on this one would be back in the cell days of analog. Bottom one, digital. If you don't have a repeater, you'll see the little noise there. It can actually be distorted. Digital signal can be distorted by noise. Then that noise can be repeated on throughout the signal. Latency, you've heard of this term, any gamers in here? Latency? Latency is basically the delay between your signal transmission and you receiving it. So when I taught high school, we used to do, I think it was Counter-Strike, and the students had to create, the deal was they had to create a level of Counter-Strike in C++, which took about 6 weeks to 8 weeks to create. Then I would let them come in and do a LAN party using the level they created. And if they would bring their own switches in. I showed them how to set it all up and everything. But we would talk about, say one student was sick that day, we might be able to patch them in through the internet to come into the room. Well, the latency of that student coming into the room versus the latency inside of the room, totally different. They're like a lame duck coming in, they're dead. So as soon as a student literally connected outside, say they were home, connected outside, as soon as they got in, they were already dead before they even before they got a chance to even look up. And so, because latency would kill you in a first-person shooter game. Same thing with networking though. Latency can cause a lot of problems when it comes to data download, data upload, and some of the causes. The length of cable that's ran could be too long. It could also be bad cabling. It's going, cabling can go bad. The devices going bad that are connecting, the switches can go bad as well. Round trip time is the other one we're going to talk about here in a second in the ping lab. Basically what that is the time for the packet to go from one sender to receiver and back. It's measured in milliseconds. So it's like me throwing a tennis ball to you and then you throwing it back would be the round trip time. So if you're Google and I'm here in Rock Valley College and I throw a ball to you and you're Google web server and when you bring it back to me, that's how long it takes round trip time for you to come back. And it's literally quick as clicking a mouse on a link to determine that. Also, transmission times can be or problems can happen because of transmission errors. So, physical characteristics in all of the media we talked about: throughput, cost, size and scalability, connectors, and noise immunity. So I'm going to forward fast because I want to get to the lab. So I'm going to skip all this here because I do want to cover a couple things of makeup of cable, and that's it. So I'm going to hit coaxial. Okay, coaxial, in the center of a coaxial cable, and by the way, it's the same type of cable you have for your cable at home. In the center is your conducting core, then you've got your usually PVC or Teflon after that, a branded shield, and then a sheath around it. This one is very efficient, coaxial is, used a lot in back when networking first started with like bus topology and ring topology. And you literally had NIC cards that would connect for these. Today, though, not so much used. We use coax or Cat5 cable more, but this is still used for networking throughout the world in a number of places. Coaxial's high noise resistance. Advantage over twisted pair, which we'll talk about, is it carries signals farther. And again, because of the makeup of the cable, is much more strong. It's stronger, more efficient. Disadvantage: it's more expensive over twisted pair. And there's hundreds of specifications for coaxial. Different types of coaxial measured by what's called AWG, American Wire Gauge, RG6, 8, 58, and 9. And you've seen this one on the left probably at home. That on the right was what we used for the network connection on the NIC card. It's called BNC connector is what it looked like. Twisted pair, we're going to be doing this in a few weeks. Maybe next week, I can't remember. Next week or week after. Twisted pair basically has 4 twisted pairs, and you'll notice it has a solid and a stripe, each color. So you've got an orange, blue, green, and red stripe in there. And so these are all intertwined, connected together, and 0.4 to 0.8 millimeter. These are encased in cheaper plastic than the coaxial. More twists per foot, the better, because it gives you more resistance to crosstalk. Higher quality, more expensive though, the more twists you have in a cable. Twist ratio refers to how many twists per feet or per foot, meter or foot. High twist ratio, greater attenuation, data attenuation, and higher noise resistance. Hundreds of different designs on twisted pair. Twist ratio, number of wire pairs, copper grade that's inside of it, shielding type, shielding materials. I've seen some that are really brittle. There's some that are really easy to work with. 1 to 4,200 wire pair possibilities. The standard is TIA EIA 568. You'll actually see it on the wire when we do it. You'll see the standard on the wire. Category types for twisted pair. is 3, 4, 5, 5E, 6, 6E, and Cat7. Cat5 and Cat5E is the most popular today in LANs when you're creating cable. And at home and work and even here, we have the Cat5 family. Advantages over coaxial, relatively inexpensive, flexible, easy to install, whether you make your own or go buy cable, either one. It spans significant distance before requiring repeater, about 150 feet is what I recommend. Accommodates several different topologies. Handles current faster networking transmission speeds, which are up to a gigabit per second. 2 categories, shielded, twisted, and unshielded, twisted. Shielded looks just like this, very well insulated. You've got the 4 twisted pairs, the foil shielding around that, the branded copper shielding, and then a hard plastic jacket around that. Untwisted, you can just tell by looking at it, much cheaper, right? You've got the 4 twisted wires, and then a nice plastic sheet around that, and that's it. That's all you got. No additional shielding. This one's much more expensive, or less expensive, less noise resistance than the others, but it's the most popular, by the way. And Cat5, Cat5E. Cat5 is what we have here. That's going to be the most expensive, or the most inexpensive, and the most common. Cat5 untwisted UTP cable with pairs untwisted, and you'll be doing this when you do the lab. And there's a certain order you have to do them, put them in order before you crimp them in the RJ45. And so when you're comparing the two between different STP and UTP, throughput about the same, cost varies a little bit. Noise, STP is more noise resistant because it's a better shielding around it. It's got the copper, it's got the extra foil, and the plastic around the entire thing's a lot more expensive, a lot better. UTP, the untwisted, is subject to difficulty offset by noise. Size and scalability, about the same, 100 meters, and so, roughly about 150 feet is what you want to go on that, max. The connectors for shielded and untwisted is RJ45, the jack there. RJ12 is what's used for old analog phone cables at home, and this is RJ45. So come the terminologies, patch cable, relatively short cable used in IT to connect computers together for troubleshooting, things of that nature. Proper cabling termination techniques, basic requirement for 2 nodes. And again, that could be through the switches you're using, the hubs you're using. Poor terminations, an example would be bad crimping of the RJ45 on the cable could cause bad noise or a lot of noise and bad connection. And then the 2 standards, 568A and 568B. The one we're using in here and most businesses use is a 568B standard, which makes up basically there on the left and right, the 568A there on the left, 568B on the right. And so combination of the 2, all right, make a straight cable or crossover cable, and combination of either one together can make a straight cable, which we'll learn more about that this semester. But basically, you'll notice on this one here, you've got an A and you've got an RJ45 terminations, and what's happening here in the middle, where the lines are being crossed over, on 1 and 3, 1, 2, and 3 actually, on the left side, 1, 2, and 3 on the right side, sorry. And what's happening here is it's causing this type of crossover cable can be used in place of having a switcher or a modem in between, or switcher or a router in between. So I can 2 computers, use a crossover cable that's wired like this, and I can talk to that computer without any switch or hub in between. Here's some of the tools we'll use: wire cutter, wire stripper, crimper tool. Then on the left is the stripper for the wire, crimper tool on the right. And we'll talk about places you can buy them here in town. They're not real expensive. After making cables, we'll do this. There's a tester that we use. You literally plug the cable in, turn the tester on. It'll tell you if it's good or bad, and it'll also tell you the length of the cable as soon as you plug it in. We'll end on this one. Fiber optic can either have glass or plastic as its mode of transportation in the wire at the center. As you can imagine, glass is going to be more expensive. For most businesses, are going to be doing the plastic, but transatlantic or long gates of fiber is going to be glass to be more efficient and last longer. And the way it works on transmission on fiber, unlike other types of transmission mediums like Cat5 and coaxial, it's light pulses being sent from laser. LED light emitting node through the central fibers going through. The cladding can be layers of glass or plastic surrounding fibers, different density from glass or plastic, and reflects back to what's called the core, and it can bend, you can move it, you can go through it, turn it, and no problem, it'll flow through there just fine. It does allow you to bend on that. It has a plastic buffer, outside cladding that help protect the core, Kevlar strands surrounding the plastic, and the plastic sheet covers Kevlar strands. All right, picture one. There's a picture of one, what it looks like. Okay, you'll get one up close and personal, by the way, when we do the Cat5 lab. Ping lab, fun time. So on that piece of paper I gave you, we're going to do that in just a second. We have a one little reading to do on ping and tracer, and then we'll go right into the lab. And you've already submitted your name, right, in the lab? Okay. So let's look at this on the overhead, if you wouldn't mind. And by the way, this document is in the lab folder as well, but I put it in here so we could read it. Okay, so ping and tracer. Come on. So ping and tracer are utilities that can be used to troubleshoot a network or internet connections. The ping utility tests responsiveness between two hosts. You can ping yourself, by the way, as a computer. You can ping yourself with ping localhost, the word ping and the letter and the word localhost, which we'll do in a second. The tracer utility checks responsiveness of the trace to trace a path as a packet goes from one host to the other. Some device on a network will not respond to ping or tracer if they blocked it. So like a lot of web servers will block pinging, so they won't get a ping of death and you heard that in that video last week, I believe. Also, pings are used in networking a lot to see if a host is reachable. If a ping doesn't come back, that's not a good thing. Or it's slow and it's come back. It's not a good thing. Ping and tracer utilities are built into Windows, Mac, and Linux, all three. Ping, the third paragraph there, is used primarily to find out if a computer is reachable, as I mentioned earlier. It accomplishes this by sending out a special packet called an Internet Control Message Protocol, ICMP, echo packet. The ICMP packet has special IP messages that are used to send information between the two hosts, like computer, router, switches, etc. When a machine receives it, it responds with an echo statement. And here's a response type of statement. So if we ping apple.com, it could come back with, okay, that's the IP address of apple.com, 17.240.0.91. And it's pinging it with 32 bits of data, which is common. And it took 70 milliseconds, and it lives on there for 46 hops, which we'll talk about what that is. Once the echo receive is sent every second, or once one is sent every second to apple.com. When it comes back, in Windows world, it gives full responses. In a Linux world, it gives unlimited responses. You have to kill the command with a Control-C command. And you can, by the way, at the end of a ping command, export that ping to a text file, a whole bunch of things you can do with it as far as, the data itself. The IP address of the echo reply comes from the domain name apple.com, the DNS name, the number of bytes it was sent, round trip time it took for the packet to go from my computer to the Apple and back, and then the time to live field. Every packet gets sent out as a time to live field which is set relatively high. The highest it can be is 255. As a packet travels over the network, the TTL decreases for every node it hits. So an example would be, if I pinged apple.com right now, it could literally hit hundreds of different nodes in between, meaning different routers in between me and Apple's web server. Every time it hits one of those nodes, it decreases the TTL. Once it gets to 0, it drops it. The packet's discarded. The main purpose of this is so the packet doesn't live forever on the network, and it will eventually die. If the TTL field varies in successive pings, like between pings 1, 2, 3, and 4, it could mean it's just looking at different routes it's taking throughout the ping, which can happen. It could also indicate, though, that the routes are experiencing problems, like the routers are having issues. If it's an internal ping, that we do a lot of times to determine the health of our routers and switches. If there's differences in ping, 1, 2, 3, and 4, in the TTL, that could be an issue. And sometimes it could be a bad router or bad switch that needs to be replaced. The next paragraph, the time field is an indication of round trip time to get a packet to the remote host. The reply is measured in milliseconds. In general, if the round trip time is under 200 milliseconds, you're good. Generally, though, that's not so good. 200 milliseconds is a long time in pinging. The time, most average is, under 5 milliseconds. A good one, we'll do in a second. When we do our local host, it's 0 milliseconds. So the time it takes the packet to reach its destination is called latency. If there's large variance in round trip times, the network may be experiencing problems. So what we're going to do now is I'm going to switch on my screen here, and I'm going to stop this.